Welcome back to the last presentation of the evening for Channel B. Thank you for attending the Departments of Mechanical and Electrical Engineering Senior Design presentations. Our last group, the Baja Four-Wheel Drive Group, advised by Dr. Vern Ulrich, will be presenting. The team members include Emma Bentz, Grant Cole, Zach Dunkley, Haddon Fox, Luke Johnson, James Laurie, Timothy McCluskey, Justin Panzarella, Thomas Snyder, and John Weiner. The first speaker for this team, go ahead.
Good evening and thank you for joining us for tonight's Senior Design presentations. We will be presenting on the 2021 SAE Baja Capstone Project. My name is Emma Bentz and I'm the team leader for this project. As you may have realized by now, my portions of this presentation have been pre-recorded. Along with 5 other members of my Senior Design team, I am currently in Tucson, Arizona at the Nationals SAE Baja competition. Our pre-recorded sections will be integrated with the rest of our live presentation. Our team was tasked with providing the Grove City College student chapter of the Society of Automotive Engineers, or SAE, with a durable car for competition in SAE's Baja Collegiate Design Series competition, which challenges engineering students to design and build a single-seat all-terrain vehicle that is reliable, maintainable, ergonomic, and economic. This vehicle competes in national competitions against other top-tier engineering programs in events that can include acceleration, hill climb, sled pull, suspension and traction, maneuverability, and a 4-hour endurance race. Shown here is Grove City's previous car, Lady Liberty, and her suspension failure at the 2019 Nationals competition in Rochester. Working with the Grove City SAE Club, the senior design team developed a product design specification, or PDS, to merge club requests and the competition design constraints. Our top vehicle goals included selectable 4-wheel drive to meet new requirements for the 2022 competition season, easily serviceable components by club members, individual components that are able to withstand max forces at national competition events, and a frame intended to last 6 years, or 12 competition cycles, plus testing and validation. All of this needed to be completed in time for the 2021 competition season. In the next few minutes, my teammates will present specifications, research and development, design, manufacturing, and validation for various vehicle subsystems.
So the chassis sub-team sought to produce a frame like that of Lady Liberty, one of the club's previous cars, while providing convenient mounting for new suspension points and adhering to all SAE Baja requirements. By PDS 4.1.1, the vehicle is required to accommodate drivers ranging from 5th percentile female to 95th percentile male, which can be seen in the chart on this slide. In regards to the steering wheel placement, angling the wheels at 23 degrees allows for comfortable wrist rotation while steering, which will eliminate strain on the drivers. Additionally, the location of the wheel center was chosen after careful measurements of varying driver sizes to allow drivers comfortable control of the vehicle without the steering wheel inhibiting vehicle egress. Placement took into account the need to easily reach the wheel with wrist restraints on. These design choices accomplish the requirements of our PDS 4.3.1 and 4.3.2. PDS 4.3.1 requires an ergonomic driver interface that allows drivers of a wide range of sizes to pilot the vehicle or extend periods of time with no significant discomfort. The seat has been designed with similar dimensions to previous racing seats used by the team. Based on input from those who have driven the vehicle, the seat is sufficiently comfortable for completing SAE endurance races. The seat back plane shall be inclined between 65 and 90 degrees from the horizontal as viewed from the side. The seat bottom plane shall be underneath the driver and be horizontal or generally sloped such that the leading edge of the seat bottom plane is level with or higher than the intersection with the back plane. Seats may also include material oriented vertically along the side of the seat bottom plane. The seat back plane is inclined at an angle of 10 degrees from the vertical in the planer and the planar nature of the back and bottom of the seat have been verified through rules inquiry. The kill switch for the car was placed in such a way that it would be easily accessible to the driver, yet would not be able to be flipped by being accidentally hit by the driver's arm or leg. The brake and gas pedal were designed with the goals of correcting certain drawbacks that the Baja team members found with the previous pedal design. A square steel plate is used as the foot contact. This results in decreased foot slippage and makes the pedal more comfortable to use because it has a larger flat surface area. The chassis was designed such that the engine and the drivetrain would be accessible and be able to be removed easily when needed. This is important for the repairs and maintenance of the Baja car. Now I'll hand it over to Tim to discuss chassis design.
Thank you, Jamie. Our tube frame was designed in Creo using a skeleton of points and sketches to form an FEA beam model of the frame. 9 studies were conducted on the frame and used to iteratively optimize the frame for strength and weight reduction. 5 of these were impact studies that used 5G accelerations, masses, and strategic constraints to apply the loading to the frame. These are useful for assessing the overall performance and function of the frame under extreme impact scenarios. 4 of these studies used vector forces generated by Creo Simulate in the design of the suspension components, and these are useful for more local or detailed stress analysis of the suspension mounting locations. The frame has been designed to be highly stressed while avoiding any and all failure in the structure. This has allowed us to keep the vehicle lightweight and achieve competitive speeds while racing, and still avoid any catastrophic failures in the structure. The final product is a front braced style frame and constructed of 4130 chromoly seamless aircraft tubing. The overall frame height is 4.5 inches taller than the previous car, known as Lady Liberty, to provide additional driver clearances and room for a drive shaft to pass under the driver. This means the frame provides sufficient height and space to protect our design riders as tall as a 95th percentile male or 6 foot 1.5 inches. Despite this additional height, the total design weight is 65 pounds, an approximate 13% weight reduction from the design weight of Lady Liberty. The fully welded, untabbed frame weight was 65 plus or minus 0.4 pounds. After the addition of 14 pounds of mounting tabs and bracketry, the final weight of the fully welded structure came to 79 plus or minus 0.4 pounds, which is still an approximate 1.5% weight reduction from Lady Liberty. Ultimately, the frame provides effective mounting for all suspension, drivetrain, and shielding components. The security of these mounts allows for a quality final product that is capable of withstanding driver abuse. Next up is Alden. Thank you.
Thank you, Tim. The frame was designed with easy fabrication in mind. The tubes were notched using the plasma cutter and then assembled with the TIG welder. Bends were avoided wherever possible in order to speed the notching process, since bent tubes cannot be notched on the plasma table. The frame came together in sections and no jigs were needed. Coplanar tubes were first tacked, and then these planes were tacked to form a 3D frame. The dimensions were verified, and then the frame was fully welded, with special attention being paid to preventing warping during the weld. During this assembly, we were able to hold general tolerances of about 1/8 of an inch and angle tolerances of 1/2 degree. It is important to us to verify that our models of the chassis match the final result. SAE requires that those welding the frame make weld samples that can be tested for strength and weld penetration. These samples passed our test with flying colors, and we are confident in the strength of the welded joints of the frame. We have plans for further verification tests to be performed on the frame by adding static loads to critical points, including the seat mounts, the seat belt mounts, the suspension mounts, and the engine mounts. The deflection in those areas will be measured using dial indicators. Dynamic testing will also be performed during drive days. Strain gauges with data acquisition units will be used to get an idea of the stresses experienced in the frame in real-world scenarios. The data gathered in these tests will then be compared to our FEA studies and frame calculations. With the deadline of the competition in Arizona, which is the ultimate trial of the entire vehicle, we ran out of time to perform these tests. They will both verify our design and provide information for the designers of the next Baja car in a few years. So we will strongly encourage members of the SAE Club on campus to run through these tests in the near future.
Here you can see some of the requirements for our suspension per our PDS and per the SAE rules. Note that it had to have sufficient ground clearance and also had to allow for very tight turns. That tight turning radius so far we've not been able to achieve with the current design, however we are in the process of researching how it can be improved.
In terms of design specifications for the brakes and steering components, we had requirements that came both from our product design specifications and SAE Baja rules. First, we had requirements for brakes that they must both operate through final drive as well as lock up the wheels when applied. That is, stop rotation of all four wheels with the car moving at full speed on a tractive surface, such as concrete. This ability is required by the SAE dynamic brake test. In terms of steering specifications, our PDS requires that steering must be compatible with drivers of varying sizes. This specification was met as we ensured that drivers of different physical builds were able to handle the vehicle both comfortably and safely. Furthermore, the steering wheel had to be placed such that it would not obstruct the driver's view of the track ahead of them and must resist slip. As already mentioned, we have validated that steering is compatible for drivers of varying sizes, though we have not yet conducted a validation test to determine if the wheel met our specification of resisting slip. This will be met in a coming validation test, as will be described later on in our presentation.
Part of our research and development for the car involved deciding which tire sizes we were going to use, which we did via selection matrix, as well as taking one of our old Baja cars and drop testing it with strain gauges to find loads experienced by the suspension members. Before moving into Creo, we modeled our suspension geometry in Lotus Shark software, which allowed for easy analysis of the kinematic responses of the suspension to certain things like steering and bump, and it allows us to track changes in things like camber and caster, which affect how the vehicle corners and remains stable during travel. On the right, you can see a graph of our turning radius versus the steering rack travel as projected by Lotus. In addition to the drop testing we did with the yellow car, we also made a dynamic simulation in our Creo CAD software, which allowed us to model certain scenarios where the car would, say, hit a log or fall off of a jump. And that translated into the force graph you see on the right, where we can look at each pivot connection and see what forces are acting on it during each scenario. Here you can see examples of some of the finite element analyses we ran on some of the suspension components. We have an upper wishbone from the front suspension and the trailing arm from the rear. And the legends show the stress concentrations in each part near junctions and especially around the shock mounts.
Grant Cole here. While designing the brake system, we set goals of low weight, low complexity, and a small number of components. We also sought to decrease the front to rear braking bias in comparison to our previous car in order to more reliably lock up all four wheels as required by SAE, and we collected data using methods including FEA during the design process.
Here you can see our front suspension. Note the double wishbone design and the knuckles with bearings within them to allow for drive shafts for the four-wheel drive train. And here's our rear suspension. Note the trailing arms and control arms. This is a very robust system that Grove City Baja has used for many years successfully on several iterations of our cars.
In terms of design of the steering components for our vehicle, we sought to implement a steering column that utilized two universal joints. This allowed us to modify the angle of the steering wheel to ensure driver comfortability. The final angle of the steering wheel ended up at 23 degrees from vertical, an angle which is comfortable for handling the vehicle without undue strain on the driver's wrists. Another necessity of the design process was to find a way to distribute loading between the steering rack housing and the frame. In past years, we have run into issues with the steering housing failing at the bolt holes, as well as bent steering racks. As a result, we sought out a different design with a profile-shaped mount that fit closely around the steering rack housing. Mount parts were carefully cut on a CNC plasma table and then welded together with precision to ensure that loading is evenly distributed on the outside of the housing rather than just around the bolt holes. Furthermore, the steering mount was designed to mate with the front differential mount through a welded point on the tabs protruding from the bottom of the mount. This further ensures stability and rigidity for both elements of the vehicle.
We settled on a 3-caliper brake system design with a caliper on each front wheel and inboard braking in the rear. We designed and manufactured some modifications to the Honda rear differential and mounted the rear brake caliper on the differential case. We also selected rotor and caliper piston sizes based on the need to decrease the front to rear braking bias, as previously mentioned, and we achieved a front to rear ratio of 61 to 39 as opposed to 68 to 32 like we had on the previous car. Here are the models of the brake rotor mounting hub and the main rear differential body, both of which were manufactured from 1045 steel. Here's the model of the brake rotor, which was plasma cut from 4130 steel, and the modified portion of the aluminum differential case.
After the Arizona race, we would like to perform some validation testing on our car. Specifically, we would like to perform a multifactorial experiment wherein we can analyze the response of the handling characteristics of the suspension, such as roll and turning radius, by adjusting certain aspects such as shock pressure, driver weight, the speed of the car, and that will give us a good picture of how our suspension responds to different driving conditions, which will lead to our ability to make more informed improvements later on the car. Furthermore, we'd like to take this car on a mock endurance track with a strain gauge setup to get a better idea of what loads are actually going into the suspension members as opposed to our controlled drop test or the Creo simulations, which are idealizations.
Additionally, in terms of validating steering design choices, we seek to further test our turning radius now that modifications have been made to steering elements. As was mentioned in our specifications section, we initially failed to meet our objective of a maximum turning radius of 10 feet at 4 miles per hour and 20 feet at 20 miles per hour. After the vehicle did not meet this specification, modifications in steering were made to substitute the steering rack for one with a longer travel. The results of these changes will be tested using a designed experiment to ensure our specifications are met. Finally, in order to ensure that the steering wheel slip specification is met, in coming semesters, we will conduct an experiment designed to measure the coefficient of friction of the steering wheel in varying conditions. These conditions will seek to simulate conditions a driver will experience throughout a typical race, which include rainy and muddy conditions. This designed experiment will be able to ensure that the steering wheel properly meets our design specifications and will provide the driver with adequate grip, no matter the driving conditions.
Our plans for validating the brake system consist of bringing the car to high speed on various surfaces and applying the brakes to see if the wheels lock up. With the recent completion of the car, we have been able to test the brakes in this way and achieved excellent results. We will also apply a 450-pound force to the brake pedal and measure its deformation to ensure it can withstand the forces required by SAE rules.
So I'll be talking about the specifications for the transmission. The first one is required by SAE that the transmission has if it has a vent, that it does not spill any hot oil or any substances onto the driver or the engine components. We satisfy this requirement by not putting a vent in the transmission. The second one requires that the transmission not have any pinch points where someone could get their clothing or fingers pinched in turning gears or similarly moving machinery. And we accomplished this by completely encasing the transmission in an aluminum clamshell design case. Finally, the last thing that the requirement that we set for ourselves was in order to attain the goal speed of 35 miles per hour, top speed, the transmission would have to be a ratio of about 2.5 to 1, which we accomplished.
SAE rules and our PDS require that our drivetrain is capable of providing power to all four wheels. We chose to meet this requirement under SAE's criteria for a selectable four-wheel drive vehicle. SAE rules also require that all drivetrain components rotating faster than wheel speed are fully shielded. We have met this requirement through the use of a sheet metal shield over the front drive shaft and a solid aluminum bell housing over the rear drive shaft.
The rear axles and hubs did not require any specifications from SAE, and as such, they were only limited by restrictions put forth in our own PDS statements, and we were able to easily meet all of the requirements.
So there was lots of thought that went into the drivetrain configuration. We actually started this process about a year ago. The first one we did was we used a decision matrix to decide what kind of configuration we wanted for the full drive system. You can see an example of one of these design matrices here at the bottom left of the screen. We considered multiple different setups, including drive shafts with U-joints, a tank tread design, multiple gears, different things, even portal axles, and eventually we came out to the conclusion that we wanted a transmission with 3 gears and a drive shaft with 2 U-joints in it. After that, there was some deliberation on replacing the gear transmission with a belt drive, and we used a decision matrix on that as well and decided to go with the geared transmission, which had already been designed during the previous semester. We took those designs from the previous semester and analyzed them thoroughly with FEA, which you can see an example of on the bottom right, to make sure that it would do what we needed it to do. We used a similar decision matrix process when looking at the various Lovejoy couplings, which is in the rear bell housing, and the differential placement and such things like that.
The main goals of the rear hubs and spindles were to reduce part count by combining the two functions into one single part. We also wanted to minimize manufacturing time of the CV axles by implementing the standard Honda spline that is found on the end of the CV axles into the rear hub. And we would further reduce manufacturing times of the CV axles by including a D shaft, which allows us to loosen manufacturing tolerances and also allows us to decrease the number of unique axle lengths. And constant updates to FEA ensured the success of the rear hubs in multiple load cases, and calculations based on torsion were done to maintain the integrity and resilience of the CV axles.
So there are 3 main things that the transmission has to accomplish. First of all, it has to deliver power to the rear drive shaft via the rear bell housing, and also to the front drive shaft via the 4-wheel drive coupling, which we sourced from Honda. In doing so, it has to direct the power around the large CVT pulley, and all the while reducing it with a ratio of about 2.5 to 1. The case was determined that it should be manufactured out of 6061 aluminum, and the gears were made out of 4130 steel, which is a very hard steel, and it was also hardened after they were cut out. The case was CNC milled, but the holes in the case were cut out on the electromagnetic discharge machine to ensure precision and accuracy, as well as the teeth on the gears. They were also cut out on the EDM machine. There were a couple of various additional parts, such as shaft caps, that were cut out on the plasma cutter in order to save time. Here you can see just a couple renderings of the transmission. At the top right is a really good view of the gear train. The middle gear and the gear on the right are identical, so they're interchangeable, and that reduces the design and manufacturing time. The top left is a good isometric view of the whole thing as it's put together, and the bottom right is a nice section of view.
A Lovejoy style coupling was designed to serve as a rear drive shaft. This coupling transmits power from a transmission output gear to a modified Honda bevel gear, which serves as a rear differential input shaft. The transmission side of this Lovejoy coupling is bolted directly to the transmission output gear and features a surface which fits against an oil seal and output bearing located in the transmission housing. An iterative process with FEA was used to reduce the weight of this component in the design phase. A solid aluminum rear bell housing was designed to align the differential to the transmission, hold the bearing required for the rear differential input shaft, and protect the Lovejoy coupling from dust and water. A front drive shaft was designed to transmit power from a Honda four-wheel drive coupling to another modified Honda bevel gear, which serves as a front differential input shaft. Since the inputs to the front and rear differentials are offset, two U-joints were used in the front drive shaft to account for this misalignment. Keyways are used to hold all front drive shaft components together, and a flanged connection is used near the four-wheel drive coupling to allow for disassembly of the drive shaft without requiring the removal of the rear drivetrain or front differential.
So the main design factor of safety we decided on for the rear hubs was at least 1.3, while still fulfilling the previously mentioned criteria. In the process of ongoing FEA, it became necessary to include a steel insert within the body of the aluminum hub to ensure the integrity of the Honda spline. The rear bearings that hold the rear hubs in place were ordered from Baja bearings, and the CV axles, with the initial goal of making a universal axle, was not met. Instead, as mentioned previously, D shafts were designed and implemented, which allowed for looser manufacturing tolerances and fewer unique axles in terms of length. They can be adjusted to fit in multiple positions, and this further reduces the manufacturing time. Here you can see a couple pictures of the design of the rear hub and the steel insert that fits into the rear hub, along with a CV axle on the right. So next, manufacturing of some of the drivetrain. The transmission manufacturing process went as expected, except for the case needed to be remade due to a bolt circle that was in the wrong position, and then it had to be remade again due to insufficient data on previous proprietary hardware that we were implementing into our design. The hubs were manufactured mostly on the CNC mill out of a solid piece of aluminum. We then cut the spline on the wire EDM and turned the face on the CNC lathe. The bearings that we are using were not modified from the stock part that we ordered, and the CV axles were manufactured by cutting stock axles in half, milling a flat section on the ends to include the D shaft. The materials that we selected for the rear hubs were 7075 T651 aluminum with 4140 steel inserts. The rear bearings from Baja bearings are made of steel, and the CV axle stock was made from 4130 steel tube stock.
So here's a couple pictures of the transmission results that we have. On the left, you can see the gears as they were cut out and as they will be aligned. They came out really nicely. And on the right is a close-up of the case and the various holes and things that were cut into it.
To validate our transmission design, the transmission was checked by hand once it was assembled to verify that it functioned as designed and to check for interference and binding in the gears. The transmission has been installed on the car and tested on our test track to verify that it functions as intended with the other components that it attaches to. After testing, the transmission will be disassembled and checked for damage or wear. To validate our drive shaft design, a test using a battery-powered strain gauge which attaches to the front drive shaft may be used to more accurately calculate the torque seen at this location in the drivetrain. This data would then be used to update our drivetrain loading calculations and perform design modifications to the drive shafts for further weight reduction. This would also help with other future modifications to the car. Testing for our hubs and CV axles will be conducted by installing battery-operated strain gauges and comparing the calculated stresses from the results of the strain gauge test to the stresses seen in FEA. Bearings will periodically be checked for wear, but we are relying on Boca Bearings quality control.
In the fall semester, we projected the cost for our car of $8,760, including components purchased in spring of 2020, including a new CVT and shocks, as well as labor. The estimated total cost for the vehicle came to $12,926. Over the course of the 2020-2021 school year, our team spent $9,493, $107 shy of our total budget of $9,600 from the SAE Club Engineering Department allocation and sponsorships. Despite COVID restrictions and quarantines, which added complexity and led to manufacturing delays, our car was indeed completed in time for the 2021 competition, thanks to the hard work of our highly motivated team. The photo on the left pictures our final vehicle, completing our car on time with a full week between final assembly and leaving for competition. We were able to perform preliminary evaluation of goals, including frame and component weight measurements, interference fit and check, and a test drive. Before competitions, final adjustments were made before packing the car for transit to Arizona. We are eager to continue validation of our specifications through competition performance this weekend. We would like to thank our fantastic advisor, Dr. Yu, our wonderful machinist and electrical support from Jim, Mrs. Henley, and Mr. Gillette, our department chair, Dr. Klaus, and the rest of our mechanical engineering professors, and the Grove City Baja Club for their generous support. We also greatly appreciate the partnership and financial support of our corporate and alumni sponsors. And thank you for joining this remote presentation. We will now take questions.
I guess I'll start us off. Maybe I missed it, but what design changes were implemented to assure that this new car would not experience a similar suspension failure as seen with Lady Liberty?
So for Lady Liberty, the A-arms were originally solid, but then as a method of lowering weight and attempting to make a faster car, they drilled holes in the A-arms. We have learned from their mistakes, and we will not be drilling any holes in our A-arms this year.
Question for transmission team. How did you wind up settling on a mechanical drive transmission? I know working on that project last year before it kicked off as a senior design project, we were kicking around a belt idea. And I guess also speak to how you settled on a CVT as your initial drive as opposed to a manual transmission as I've seen in other cars.
Yeah, so for the CVT, I don't remember ever deliberating on whether or not we wanted that or a manual transmission. If we did, it was kind of decided upon pretty early. There was a lot more time and effort that went into figuring out what to do after the CVT, as you know. The main reasons we went with a mechanical geared transmission over a belt-driven transmission, one of the biggest ones was that the lower belt pulley would have had to have been much larger than the upper one, and it would have caused significant ground clearance issues and clearance issues with the full drive coupling and things like that. And we determined it really just would not be worth the effort over the gears. Does that answer your question?
It does. Very impressive design you guys have here. I've sort of been seeing this unfold slowly. I'm pretty close with a lot of the members of the team. There's pretty impressive work you guys have accomplished here.
Thanks, Isaac. Appreciate it. Are there any more questions?
Yeah, I have a question. Are there any components that you're particularly concerned about in terms of durability on your current design?
Yeah, so there's one in particular that I know of. We had to modify a stock Honda part. It's a shaft that goes in the four-wheel drive coupling, which when turned on engages four-wheel drive. When turned off, it's just two-wheel drive, the car is. But anyway, there's a shaft that comes out of that would normally go into the differential. But because we put my transmission and Justin's bell housing in between the four-wheel drive coupling and the differential, it had to be modified. And so comes from the factory. It was very, very hard. And we had a difficult time machining it, but it got done. The problem is it's not really designed to be the shape that it is. So that would be one of the main points of failure that we're watching out for.
Could you guys talk a little bit about any challenges with synchronization or traction control with this four-wheel drive system?
There isn't traction control. We have a welded diff in the front, and I believe it's an open diff in the rear. There's really not much sophisticated traction control going on other than that. The four-wheel drive is switched on and off via a switch, just like it would be on the four-wheeler that the coupling came out of. Does that answer your question, Dr. Brooks?
I think so. So just so I understand, so you're saying you can basically turn on the front drive. That's the welded differential.
Yeah.
You just turn it on or off, right?
Yes, sir. It's electrical. It's a switch.
Okay.
Yep.
And then so I know how basic differential works, but I don't know how that works between front and rear. You know, are there any with the front wheels engaged? How does that handle it? Do you have any synchronization issues? Meaning, you know, the front wheels are pulling harder or fighting the back wheels if there's any slight misalignment in the gear ratios or anything?
So when the four-wheel drive is disengaged, the drive shaft that runs to the front axle and the front axles themselves are not turning. The problem with that is normally that would prevent the front wheels from turning as well. What we decided to do about a year ago was put one-way bearings in the front wheel hubs, which is a pretty cool idea. And so what that allows us to do, the front wheels, when it's in two-wheel drive, will overrun the front axles. And then when you're in four-wheel drive, the front axles will power the wheels. Is that what you were looking for?
Yeah, that clarifies it for me. Thank you.
Yeah, no problem.
Any more questions for the Baja four-wheel drive team?
I have a quick question. Any news on how the team is doing? Competitions? Any updates?
As of this morning, we have information that we have passed tech inspection successfully, which is really awesome. We got through on the first try without too much of an issue. We've also passed brake test, engine test, the four-wheel drive test, and I believe they will start with the endurance race tomorrow.
Well, that's great news.
This is your last chance for a question. Well, I would like to say good job, Baja four-wheel drive team. I know that this was quite an undertaking, and the success that even getting a car pulled together and having everything pass these inspections so far is a big applause to what you've accomplished. Good work, and have a great evening. Thank you, guests, for attending, and have a good time. Bye.